Hi guys, welcome back to the CCNA video series. In this video, we are going to begin to have a look at STP, which stands for Spanning Tree Protocol. This video is just going to be an introduction to STP. So the objectives for this video are to understand what STP does, why we need STP, and what problem it resolves. So to begin with, what is STP? So STP, that stands for Spanning Tree Protocol, and it's a layer 2 protocol that is enabled on all switches by default. It's defined in IEEE 802.1d, and it solves a massive problem that is caused when we introduce redundancy into our network and redundant links. Now to see, so I'm not going to really dive any deeper, to see why we need it, let's have a look at this example. So now, can you see anything wrong with this network topology? So pause the video, take a couple of minutes. Can you see anything wrong with this network topology? I want you to pause the video now. So I'm assuming that you've paused the video and that you've identified what's wrong with this network topology. So obviously we've got 3 switches which are all connected by links. I can reach devices from this switch on that switch, etc. So we've got full connectivity. But the issue with this network topology is that we have a single point of failure, meaning if this link were to fail, that means all the devices on this switch will have complete loss of network connectivity. If this link were to fail, that means all the devices on this switch would have complete loss of network connectivity. So single point of failure means if there's a single failure, it results in a big portion of our network having network connectivity outage, which will obviously cause problems. Now, like I said before, without redundant connections, so again, imagine the 3 switch topology. Now, we have switch to switch connections, everything is good, and devices can reach each other. However, disaster strikes. One link fell, so literally one link has failed, and this maybe all that's happened is somebody's kicked the cable or someone's accidentally unplugged the cable has become loose. But all it takes is for a single link or one of those links to go down, and we have a complete network outage for a portion of our network. And obviously this isn't a very robust design because we have a single point of failure. We want to design our networks with redundancy in mind so that if something happens, our networks can still function and that the business can still function and still make money. In this network, if a single device or a single link fails, there's complete network outage. Complete network outage for a portion of our network, which means that any devices which connect to that switch cannot carry on with their daily functions, and that means that the business will lose money. Now you may be thinking, wait a minute, Abdul, wait a minute. I have a solution for this. The simple solution. All we need to do is attach another link here. That means if this link does go down, I can just use this link, or I can actually use both links to send and receive data, which means increased bandwidth. Now that is true. So to be fair, you've sorted out our single point of failure. We have redundancy. However, you have actually caused a complete network outage. You have just made things worse. And now you may be thinking, okay, well, how have I made things worse? So, first of all, let's talk about broadcast frames. And so I'm going to talk about the difference between a broadcast or Ethernet header and trailer and an IP header. So, when we looked at the IP protocol and we looked at the IP header, we saw a field in the IP header called the TTL field, or the time to live field. Now, if you go back to the video, I talked about how the TTL field is included in an IP header to stop an IP packet from looping around our network. So essentially, every time a router receives a packet, it's going to decrement that TTL value by 1. If a router receives a packet and it decrements that TTL value by 1, and then the TTL value is 0, it's going to discard that packet. Now this stops the packet from looping around our network, and that means the packet can only loop around for a certain amount of time before it's then discarded. All good, okay? However, if we look at the Ethernet header or Ethernet trailer, there is no field in the Ethernet header or Ethernet trailer that has, or which is similar to the TTL value. Okay? There is no field which is similar to the TTL value. That means that if an Ethernet frame were to loop around our network, that frame would continuously loop until we unplug the cable or do something like that, because there's nothing in that frame which allows it to expire, which allows its life to expire. Now, think about how switches handle broadcast traffic and unicast traffic, or sorry, unknown unicast traffic. Okay, so remember, with broadcast traffic, a switch will forward that port out every single interface. Sorry, a switch will forward that frame out every single interfaces apart from the interface it received that frame on. With a known unicast, the frame has got a destination MAC address. For some reason, the switch doesn't have an entry in its MAC address table for that specific MAC address. So what does it do? It floods that frame out every single port on the switch in the hope that that frame obviously gets to the correct destination host. And obviously, taking into account VLANs, it's going to flood that port out every single port which resides in that same VLAN. Now, this is where redundancy can cause an issue. So think of it like this. Imagine we take it from this point of view. Now this switch, and we're only going to go from left to right. This switch has received a broadcast frame. Good. It forwards out every single interface. Okay, so it goes all the way over here. Now, this switch has received a broadcast frame. What is this switch going to do? It's going to forward that frame at every single interface apart from the interface it received that frame on. So in this case, it's not going to forward it out this interface, but it'll forward it out this interface. Now, when this switch receives the frame, what's it going to do? It's going to forward the frame at every single interface apart from the interface it received the frame on. So it forwards it back down to this switch. Now, what is this switch going to do? It's going to forward that broadcast frame at every single interface apart from the interface it received the frame on. Now, can you see the issue? Now, can you see the issue that occurs when we introduce a redundant link into our connection? It causes a broadcast storm. Essentially, what happens is that our switches just continuously forward these Ethernet frames, these broadcast frames, these unknown unicast frames around our network for an eternity. The only way to stop this would be to unplug one of these links. And the reason being is because there's nothing in the Ethernet header or trailer inherently which is used to stop loops from occurring. Like with IP header, we have the TTL field. With Ethernet, there is no field to define the life of a Ethernet frame. And so this frame will loop around endlessly. And like I said before, taking into account VLANs, it will just be forwarded out every single port within that VLAN. So now you're thinking, okay, wait a minute. Now, for layer 2, redundancy is bad, okay? I'm either going to have all routed links, or I'm going to have to just deal with a single point of failure, because you just told me, Abda, redundancy is bad and it's going to bring down my whole network. Very true. But now, in steps STP, Spanning Tree Protocol. So, the way that STP works, it allows us to have our redundant links. In this case, we can still have our redundant link down here. However, think of it like this. STP, it drops a tree over that redundant link. So, visual imagery, a tree there. The way that STP works, it allows us to have redundant links, but not all those links will be used. So the way that this works now is that this redundant link is going to be blocked. So no traffic will be flowing over this redundant link. Traffic will be flowing over these links and these links, okay? All good. This stops the broadcast issue, because obviously that means that if I want to send a broadcast packet, it will go to this switch, to that switch, out all the ports on this switch, and will not go over this link. So that means the broadcast ends at this switch. Okay. However, what happens if this main link were to fail? Well, this is when STP steps in. So with STP, if the primary link fails, okay, and we have, obviously, we're going to have a network outage, then what STP does, it removes that tree from that redundant link, and our traffic can flow freely over that link. So that means that this link is no longer blocked. This link is now available to forward traffic. So that means even though this primary link has gone down, this switch down here can start using this link. That means that to reach devices over here or to reach devices over here, it can use this and this path. That means that now a single link failure doesn't cause complete network outage for a portion of our network. And everybody's happy, everybody can send traffic, and if you think about it, it's very, very simple in its design. Literally, we have redundant links, we block the links that we don't need at the moment. As soon as the need arises to use those redundant links, then we can. So now, taking that all into account, you may be thinking, okay, redundant links good, etc. But think of it like this. Okay, my switch has got multiple redundant links. Which links does it block and which links does it forward? Obviously, there has to be some sort of process of elimination to discover these facts, because the switch has to go through some sort of method. It's just not going to blindly block and allow some links. There has to be some sort of process in place to choose which links are best and to block the other links, and then to then block enough links to stop a loop from occurring. And so think of it like this, okay? Imagine that you work in an office, your department has got about 6 members of staff, okay? Now, obviously, every morning you guys travel to that office building. So think of that. That's your central point of convergence, okay? So that's your central point. That's where all the people in your department are traveling to, okay? Now, with that in mind, the route that you take in the morning is going to be to find where you're going to. So if you think about it, when we drive to any location, the route that we take is going to be the quickest route to get to that location. So in this case, if we want to get to an office building, we are going to take the quickest route. It's not the only route to the office building, but it's our quickest route to reach there. And obviously, if something happens, let's say there's a roadblock or the traffic jam or that route is closed off, then there are obviously redundant paths or redundant routes that we can use to reach that office building. But in the end, the members of staff all calculate their best routes to reach that building because they're all going to the same place. And that's basically how STP works. So with STP, the STP algorithm works like this as an overview. We choose one switch to act as our main switch. So that is the switch, think of that as your office building. That is the switch that all the other switches want to get to. That's the main switch. That's where everything's going down. And so we choose the main switch. And then the way the STP algorithm works, all the other switches do around our network is work out the best path to reach that main switch. That means, as an example, we may choose this switch as the best as our main switch. And obviously, you will want to choose the most powerful switch in your network to be your main switch, because essentially all traffic is going to flow through that main switch. Because all links are going to be pointing towards that main switch. And then all these switches do down here is work out, what's my best path to reach that switch? They base it on the links that they have to go through. So in this case, they would choose faster links, so links which run at a faster speed than slower links. So like how when we want to travel to the office in the morning, we choose the fastest route. It's exactly the same thing. These switches, they choose their fastest route to reach that main switch. And then what about links which aren't part of that fastest route? Then we just block those links. And if you think about it, that's exactly what we do when we travel to the office in the morning. We take the fastest path. We ignore all the redundant links until the need arises for us to use those redundant routes. That's exactly how STP works. It's literally that simple. So the algorithm as an outline. Choose one switch as your main switch. They go through some sort of election process. We can actually influence the election process because obviously we just don't want any switch to become the main switch, because you have to remember the main switch, all traffic is going to flow through that main switch. So we want the most powerful switch in our network, the strongest switch, the one that's got the most bandwidth, the one that can switch packets frames the fastest. We want that switch to be our main switch. Then all the other switches, they just calculate the fastest path to that switch, block everything else, and then when the need arises, imagine that this link over here goes down, and that's fine. I can just unblock this link and now use this path. Literally as simple as that. Yeah, so that's it. Simple as that. STP is literally as simple as that. Why we need it? For redundancy. Without it, we have loops in our network because there's nothing in the Ethernet header or trailer to define the lifespan of an Ethernet frame. So then we introduce STP, we block redundant links, and then obviously once a primary link failure occurs, then we can use those redundant links. This was just an overview to define why we need it, how it works as an overview. But please join me next time where we will dive deeper into how this election process works and how the STP algorithm works. Again, if you have enjoyed this content, then please subscribe to my channel. If you found this video useful, then please share so that we can get high quality IT training to the masses free of charge. Thank you very much for viewing.